transforming functions, graphing functions, where graphs meet. Okay, so suppose we have a set of axes like this. This is the x-axis, this is the y-axis, and imagine we have two functions, f of x and g of x. Let me use red color to describe or to denote, show the graph of the function f of x. Imagine this would be the function f of x, or function f, okay? And imagine you have a different graph. You have the graph of the function g, which would perhaps be a quadratic function and would look something like this, okay? So this would be the function g. Now, these two different functions, when they are drawn or shown on the same set of axes, will or may intersect. Okay, the graphs may intersect. In our situation, they do intersect in this point. So this is the point of intersection here. Now, what is interesting about this point are its x and y coordinates. Okay, so this point here has the coordinates of x and y. So if you look at the number f of x and at the number g of x, so f of x, it's the value that the red function assumes at this point, and it's the value y, and g of x is the value that the blue function assumes at this point, and it's also y. So you see that these two values are equal, okay? So we may use this property that f of x equals g of x at the point of intersection to solve equations graphically, but we must make sure the graphs are drawn accurately. So if you want to use this feature, this important fact that the point where the two graphs intersect is the point which satisfies the equation f of x equals g of x, if you want to use it for solving mathematical equations graphically, in using the graphical method, of course you need to have a good level of accuracy in your graph. You cannot just sketch those graphs, you have to draw them to scale. Okay, so this is the main idea, and now let us look at an example. So it's in part A, it asks us to draw the functions. So there is this verb draw the functions y equals 1 over x and y equals 2 minus x on the same set of axes with the domain from -4 to +4. Okay, so we are not going to sketch the functions, we are going to draw them, and since it's 2020, we are going to use GeoGebra to achieve that goal. So one of those functions is 1 over x, the other one is 2 minus x. So let me switch to GeoGebra, and let me first type in the function 1 over x. So y equals 1 over x. Okay, this would be my function f. It's there in the graph in blue color, and the other one would be just y equals 2 minus x. It's the linear function like this. It's the function g. So what you may notice is that the blue and the green function, actually they touch in one point here, in this point. Okay, so this graph may be helpful, and GeoGebra, this is the GeoGebra calculator, graphing calculator app, enables you to take this image and export this image. So I will export this image, copy to clipboard, okay, like this. I will just click here and go back to my presentation and Command V or try to paste it in like this. And here it is, here is my graph, okay? So this is what I had to do in part A. Okay, let me place it here. Somewhere here. Okay, so this is the graph of those two functions. Let me say that this is part A. The red function was the function f, no, it was g, and it was the function y equals 2 minus x, and the blue function was the function f, and it was the function y equals 1 over x. So the blue function is the reciprocal function, while the red function is the linear function. Okay, now we had to draw these functions. Of course, what I didn't do, as was asked, was I didn't sketch it or draw it with the domain from -4 to 4. My domain is larger. I started, well, the GeoGebra started at -8 and ended somewhere at 8.5 or somewhere like that, but don't worry too much about that. You may imagine the domain from -4 to 4, and at the domain the function looks exactly as it looks in this picture. Okay, so it's fine. In part B, we have to find any solutions to the equation 2 minus x equals 1 over x on that domain. Okay, so we have the equation in part B. Let me use the black color here. We have the equation 2 minus x equals 1 of x, and we have to find any solutions to this equation on this interval from -4 to 4. So if you look at that using this idea of intersecting functions, so 2 minus x is actually, it's the g of x, and this should be equal 1 over x, which is actually f over x. Okay, so we may use the graphical method of solution and solve this equation graphically using this picture here, and we see that these two functions intersect just in one point, and it's this point here with coordinates 1 and 1. And hence, we may say that the solution to this function is just x equals 1. Okay, so this would be the solution to the function, to the equation g of x equals f of x, or 2 minus x equals 1 over x. There is also another way how to solve equations. You do not need to use graphical methods. You may use algebraic ones. So let me do that in this second way. So 2 minus x, I will copy the equation first, is 1 over x. Okay, so first let us suppose that x is not equal to 0, because, well, the function f of x is not even defined at that value. And now let me multiply the equation by x, so I get 2x minus x squared equals 1, and then place all the terms on the one side. So let me have 0 equals x squared minus 2x plus 1. Okay, so you may see that this on the right hand side, this expression, it's actually the perfect square. It's x minus 1 all squared. Okay, or I can say it's x minus 1 times x minus 1. Now the question is, when does the product of two expressions equal 0? Well, my answer, of course, according to the null factor law, which says that this happens only when one of those factors or the other is 0. So according to that law, either x minus 1 equals 0 or x minus 1 equals 0, which is the same. So I have just one condition. This has to be equal to 0, and by adding 1 to both sides, I get x equals 1. So this would be the solution. Really the solution which is in, well, it corresponds to this one. It's the same, so it's very good. Okay, it's good for us. So we have solved it. There was also another way how I could proceed from this point on. I could also have used the usual method of solving the quadratic equation using the formula. So in this method, I would just write x equals minus b plus or minus square root of b squared minus 4ac over 2a. This expression here, the b squared minus 4ac, is what is called the discriminant of the equation. And solving it this way, I would get the following. So minus b is 2, plus or minus b squared, which would be minus 2 squared, minus 4 times a, which is 1, times c, which is 1, over 2 times 1. So I would get 2 plus or minus. Now look here, 4 minus 4 is 0, so it's the square root of 0, so it's 2 plus or minus 0 divided by 0, so it's really just 1, okay, 2 over 2, which is 1. So the discriminant in this case, discriminant was equal to 0, okay? This was the interesting fact about the solution of this equation. Now let's look at part C. In part C, on the domain x is in R, so we have the entire set of real numbers. For what values of k does k minus x equals 1 over x have one solution, no solutions, or two solutions? So again, we have somewhat an interesting situation. So in this case, we have one function, g of x, which is k minus x, and where k is some parameter, some number, and f of x is the same function as before, it's 1 over x. And we have to say for which values of k does this equation have one solution, no solutions, or two solutions. So we have to solve the equation g of x equals f of x. We have to intersect the graphs and see when, for which values of k there is one intersection that would represent one solution, there are two intersections which would represent two solutions, or there would be no intersections at all, which would represent the situation that there are no solutions. Okay, so to solve this using the graphical method, let me go back to GeoGebra and start anew. So the first function would be the function f of x, which would be y equals 1 over x. Here it is. Now I need the slider k, which would represent the parameter, and I will define another function y equals k minus x, like this. Okay, so this is the function, and now by sliding the slider, by changing the value, I see that it changes the line itself, the horizontal, the linear function line. Okay, so now let me talk a little bit about this value here, y equals 1 minus x. So this value 1 is the value that the function assumes when x equals 0. So when you substitute 0 for x, you get 1. If you have k equal to 2, for example, and substitute 0 for x, you get 2. So this point here, this number k, actually represents the intersection of the graph of the linear function with the y-axis. So it's this point here, this intersection point. So when I change the k, then the point of intersection changes. For example, when k is 1, the vertical intersection point is just 1. Okay? Now, the minus in front of x, of the variable x, represents the gradient of the linear function. The linear function has a constant gradient throughout all its values, so it always decreases at an angle of 45 degrees, and the gradient is minus 1. So it ensures that when the y-intercept is 1, then the x-intercept of this function must be also 1. These two numbers have to be equal. If k is 2, for example, and then the y-intercept is 2, and also the x-intercept has to be 2. So this should give you an idea of the behavior of this sliding function when it slides, when I change the values of k. And now you can see yourself what the answer to this question in part C is. So when k is 2, so this was exactly the situation from part A of the exercise, then we have just one solution, and that's the solution x equals 1. Okay, there is just one intersection point of these two graphs. When k is larger than 2, there for sure are going to be two different solutions. So for example, this and this. Okay, and when k is less than 2, like this, but at the same time greater than negative 2, so when it's between negative 2 and 2, like this, we get no solution at all. There is no solution. but when it's -2 or less, there is going to be solution. When k is -2, there is this value -2 here, we have just one solution, and when it's less than -2, we have two solutions. Okay, so we may now try to write it down here. What we got was the following. Okay, I will just try to write it. If, okay, let me start to do it first by first. So one solution was achieved when k was either 2 or k was -2. Okay, in these two situations, the line touched the branch of the hyperbola. For k equals 2, it touched the upper branch. For k equals -2, it touched the lower branch of the hyperbola, sorry. Now, as for the second part, which asks us for no solutions at all, no solutions are there. There are no solutions when k is between -2 and +2. So I may say that k is less than +2 and greater than -2. So this is the situation when there are no solutions. And finally, two solutions are present when k is either greater than 2 or k is less than -2. So in this first case, the linear function would intersect the upper branch of the hyperbola, and in this second case it would intersect the lower branch of the hyperbola in 2 points. Now, this was the geometrical solution, or the solution using graphical solution, but we may solve this problem also using the algebra, and this is the last thing that I'm going to show you in this video. So let me copy this equation again. So it's the equation it was the equation k minus x equals 1 over x. Okay, now if I multiply by x as before, I get kx minus x squared equals 1, or I might rearrange to get x squared minus kx plus 1 equals 0. So this is a quadratic equation, and there is a parameter k there. And you know that the quadratic equation, any quadratic equation, may have either two different solutions or one double solution, or it may have no solutions at all. All that depends on the value of discriminant. So the discriminant, which is b squared minus 4ac, as mentioned here already, okay? So the discriminant in this case is b squared, which is k squared, okay, minus 4 times 1 times c, so 4 times 1 times c is this, and that's it. This is the discriminant, k squared minus 4. K squared minus 4. And now the question is what the discriminant is. So if discriminant is positive, we may have two solutions. If the discriminant is equal to 0, there is just one solution to the equation. If the discriminant is negative, we may have 0 solutions, no solutions at all. So the only thing that remains here is to imagine what happens when. So imagine I would sketch a graph here, which would here on the x-axis have the value of k, and on the y-axis it would have the value of delta, or of the discriminant. This function is the quadratic function, and it passes through the value minus 4 here. And it should go somewhat like this. It should pass, its branches should be opened up, and it should pass through these 2 points for which the value is 0. And you may check yourself that when k is 2, you get 2 squared minus 4 is 0, so this number must be 2, and when k is negative 2, you might have also 0, so this number here is negative 2. And now look at this graph and ask yourself, for what values is delta equals 0? Well, you see it's equal for 0, it equals to 0 for two values of k. For this value, k equals 2, and for this value, k equals negative 2. So we may say that k equals 2 or k equals negative 2. So this is the situation when the function, when this equation here has, here we are, yeah, this equation here, when this equation has just one solution. And this is in line with this conclusion here, k equals 2 or k equals negative 2. Now, two solutions. There are going to be two solutions when the discriminant is positive, so when the value of this quadratic function is positive. So you see it happens for these values of k, which are greater than 0, than 2, sorry, and for the values of k which are less than negative 2. So there are two solutions when k is either greater than 2 or k is less than negative 2. This is in line with this conclusion here, when k is greater than 2 or k is less than negative 2. And finally, no solutions at all. No solution. There is no solution when the discriminant is negative, and this happens here in this interval between negative 2 and positive 2. In this interval, the graph is below the horizontal axis, so the value of the graph is, or the value of the function is negative. So we may say that this happens when k is less than 2 and greater than negative 2. Okay, so this is also in line with the conclusion which was reached here. Okay, so I showed you how to solve this using two different methods, either the graphical method, which is the most important at this moment for us, and the algebraic method, which should be familiar already from your prior studies.